you give perfect directions? It seems pretty simple, right? But just saying something is, say, 6 kilometers away, that's just not enough. To really get from point A to point B, you need a very specific language, one that describes not just the distance, but also the direction. So today, we're going to decode that hidden language, the language of scalars and vectors. So let's kick things off with a problem that shows you exactly why a single number on its own doesn't always cut it. Imagine you have a measurement and it's perfectly accurate, but you still end up totally and completely lost. I mean, how is that even possible? All right, picture this. We're out camping and I come back all excited. I tell you, I found an amazing fishing spot and it is exactly 6 kilometers from our tent. You've got the distance, you're ready to go, but which way do you walk? North, south, east? You could literally walk in a perfect circle 6 kilometers out from the tent and never, ever find it. And that right there is the whole problem. The number 6 kilometers is a great piece of info, for sure, but it's incomplete. Without that one other vital piece of the puzzle, you could wander around for hours and completely miss your destination. This is where two really fundamental concepts from physics and math come in to save the day. The answer to our little fishing problem lies in understanding the difference between something called a scalar and something called a vector. Okay, so first up, let's talk about this scalar. It might sound like a super fancy scientific word, but it's something you and I use constantly every single day. A scalar is basically any quantity that's fully described by just its magnitude, that is, a number and its unit. It simply answers the question, how much? And I mean, think about it. The length of a class period, right? 50 minutes. The volume of your car's gas tank, 65 liters. The temperature outside. All of these are scalars. They tell you how much, but they give you zero information about which way. A 50-minute class is just 50 minutes, no direction needed. And now, for the hero of our camping story, the vector. A vector takes that scalar's magnitude and unit, and it adds that absolutely crucial missing piece of information, direction. It answers both how much and which way. So let's jump back to our fishing hole. If I change what I say to walk 6 kilometers northeast, well, suddenly everything just clicks into place. You have the magnitude, that's 6 kilometers, and you have the direction, northeast. You now have a vector, and more importantly, you're going to find those fish. This chart here lays out the key difference just perfectly. A great way to think about it is this. Distance is a scalar. It just tells you how far you traveled, kind of like the number on your car's odometer after a long drive. But displacement, that's a vector. It's the straight line distance and direction from where you started to where you ended up. It doesn't care about the winding path you took, just where you are relative to your start point. Okay, so now that we've got a handle on what scalars and vectors are, how do we actually, work with them? Let's start with the simplest possible pace, doing a little math on a straight line. Let's stick with our camping trip for a bit longer. Imagine your friend starts walking towards that amazing fishing hole, but oh no, he runs into a bit of a problem. This little story is actually a perfect setup for some one-dimensional vector math. Okay, so just follow the journey. First, he walks 4.5 kilometers northeast. That's our first vector. Then he has that oh no moment and turns right around, walking 1.2 kilometers back southwest. That's a second vector, but it's pointing in the opposite direction. So to find his final spot, his final displacement, we just add them up. We can think of northeast as positive and southwest as negative. So 4.5 minus 1.2. And that leaves him at a final displacement of 3.3 kilometers northeast from the tent. And there you have it. Just like that, you've done vector addition. It's really as simple as adding positive and negative numbers on a number line. The whole point here is that direction matters. Walking forward and then walking backward doesn't always put you back where you started, unless you walk the exact same distance. But what happens when our journey isn't just a simple straight line? What if it has a bunch of turns in different directions? Well, let's scale up our thinking from a simple path to a full-on road trip. So let's imagine we're planning a big road trip through Florida. Each leg of that journey, say from Tallahassee over to Jacksonville, can be represented as its own vector with its own specific distance and direction. So how in the world do we add up all these different legs of the trip? Well, we can use a really simple graphical method. It's called the tail-to-head method. And honestly, it's pretty much exactly what it sounds like. So here's how it works with our route. We draw our first vector, our first arrow, from our start in Tallahassee to Jacksonville. Then, right from the head of that arrow in Jacksonville, we draw the tail of our next vector, pointing to Daytona Beach. And we just keep doing that, chaining them together, tail to head, for the entire trip. So after all that driving, what's our total displacement? Well, it's not the total kilometers we drove. It's a single vector. We call it the resultant, that you draw directly from our starting point, Tallahassee, all the way to our final destination, Gainesville. It represents the shortest straight line path from start to finish, no matter how we zigzag to get there. So, okay, we've defined vectors. We've even done a little math with them. But why is this so important? Why is this such a foundational concept in pretty much all of science and engineering? I absolutely love this quote from our source material because it just puts everything into perspective perfectly. I mean, you can't write a book without sentences, right? Well, you really can't do physics without vectors. They are the fundamental building blocks for describing motion, forces, fields, you name it. And their applications are literally everywhere. We're talking about calculating the forces on a bridge to make sure it's safe, navigating an airplane through the sky, creating the 3D models you see in movies and video games, even forecasting the weather by tracking wind patterns. Vectors are the hidden language that makes all of this stuff possible. So here's the bottom line, the crucial takeaway. A number all by itself is really just half the story. A scalar tells you how much, but a vector tells you how much and which way. It provides context, it gives us clarity, and it gives us the complete picture of how things really move and interact in our universe. So let me leave you with this question. Think about your day so far, your journey. And I don't mean the total number of steps on your fitness tracker. Remember, that's a scalar. I mean your displacement, the single vector from where your day started to where you are right now. What does that vector look like for you?